Good morning, folks. In this class, I'm going to basically take the next natural step, following what we were talking before in the previous class. In that class, I introduced force vibration, the concept of force vibration. We discussed how does a spring mass system respond under harmonic force excitation. Right? Now, the next natural step would be, well, let's expand this and add a damper to this system and see how can we actually study the force vibration, the response of a spring mass damper system under a harmonic force vibration. So that's what I'm going to do. Let me just put it under harmonic excitation of let's put it, let me write it this way, with viscous damping. This is a good title. With viscous damping. A specific type of damping. I'm not talking about Coulomb friction, just viscous damping or viscous damper. And I can also add to this that I'm specifically going to talk about underdamped systems. Underdamped systems. We are not going to talk about overdamped or critically damped systems. Hopefully you remember when we were talking about spring mass damper systems, depending on what is the damping ratio, which is the relationship between the damping constant and critical damping. You're going to have either an underdamped system or a critically damped or overdamped. So in this case, we'll only be focused on underdamped system, the spring mass damper system with the viscous damper, which is an underdamped system, meaning that damping ratio is smaller than 1. So let's start where we started when we were looking at the spring mass system. I have my spring mass damper now. This is the M. I have the spring connected and the damper there. Right? And it's the simplest system we can have, or simplest form of a spring mass damper system. And now what is added is that we have a F naught cosine omega t. It's a harmonic excitation. A similar harmonic excitation we had for a spring mass system. So if I draw the free body diagram, right, that's where I always start. I find the equation of motion, then I try to solve that equation of motion, which is typically a second order differential equation. So looking at the free body diagram, and kinetic diagram. And that would be the mass here. Mass is there. These two are equivalent. This would be Kx. This would be Cx dot. And then I have the force applied to the system as external force. And here we have, well, let's say the system is accelerating this way. So if I write down the equation of motion, right, summation of all the forces is not equal to 0, is equal to mx double dot, mass times acceleration. So I'll get minus kx minus cx dot plus f naught cosine omega t is equal to mx double dot. From there, you can even write it in a more familiar form, mx double dot plus cx dot plus kx is equal to f naught cosine omega t. You have seen this equation. The left side of this equation, mx double dot plus cx dot plus kx, is for a spring mass damper system when we were talking about free vibration, when there was no force involved. Now what is added is the force that is acting on this system, and in this case is harmonic force in the form of f naught cosine omega t, f naught being some constant, Newton or any other unit that you use to measure force, and omega would be the frequency of the excitation. And again, similar to what I did when I was dealing with the spring mass system, I'm going to divide both sides by m. So this becomes x double dot plus c over m x dot plus k over m x is equal to f naught over m cosine omega t. It's just rewriting the equation of motion that is more convenient for us. It's easier to deal with, or at least it's easier to interpret. This one, remember I introduced in the previous class, uppercase F naught over m. I said let's just take that as lowercase f naught. K over m, well, it's the square root, it's the squared, it's omega n squared. C over m is a new term. I'll just give you what it becomes, or the way you can write it. You can just write it as 2 zeta omega n. Feel free to replace zeta, well, zeta being C over C critical, which C critical by itself is 2m omega n. Right? Feel free to use those that equation, plug it in here, find C over m, and see that you can actually write it as 2 zeta omega n. It's relatively straightforward. So from there, the equation of motion, the form that I wanted, becomes x double dot plus 2 zeta omega n x dot plus omega n squared x becomes equal to f naught cosine omega t. And that is the equation of motion that I want, or I want to use. Right? Now, just as a reminder, I'm just going to put them here in case you forgot. With omega n being square root of k over m, you should be very comfortable with this at least. K over m, zeta being c over 2m omega n, and just let's put that here as well, just to make sure that we don't forget. F naught is equal to F naught over m. Right? This equation of motion, zeta omega n and F naught being defined that way. Now, second order differential equation, non-homogeneous. Right? If the right side was 0, it wasn't homogeneous. It was a homogeneous differential equation. Now we have a second order differential equation that is non-homogeneous. We have some parameters, a function of time on the right side. Right? You can write this as a general form of, well, this is a function of time. Right? This is some force as a function of time. So the same story, right? This differential equation is going to have a solution with two parts, the part that is related or associated with the homogeneous part, and the part that is associated with the non-homogeneous part. So the system response, or the solution in this case to this differential equation, would be x h, which is the solution to the homogeneous part, plus xp, which is the solution to the particular part. It comes into play because of that f naught cosine omega t on the right side. Now, solution from the homogeneous solution of the homogeneous part, or suggested form of the solution for the homogeneous part, is something we've seen before. Right? It's if I get rid of what is on the right side, right? Imagine that there is no f naught cosine omega t. This would be mx double dot plus cx dot plus kx equals to 0. And this is a spring mass damper system. So we actually know the general form of the solution. The general form of the solution for the homogeneous part, meaning that just ignore the part that makes this differential equation non-homogeneous, is a e to minus zeta omega nt sine omega dt plus phi. We have this from before. A and phi being constants that they have, we have to find from initial conditions. Particular part of the solution, in this case, now we have a cosine form. So you remember when I was talking about spring mass damper, I said since it's a harmonic function in cosine form, the general form of the solution, a particular solution should also be in cosine form. So I'll use the same form that I used for spring mass damper, cosine omega t, omega being the excitation frequency. Don't get this confused with natural frequency. And this omega d is damped natural frequency. Omega t. Now, one thing is added here is minus theta. And this minus theta is added there because now we have a damper in the system. And this damper, just as a general explanation, if you want to know why that theta showed up there, is that damper is causing some phase difference between the force and the response. And I have to take that phase difference into account, and that's why I put that theta there. So there's a phase shift between the system, the force input, and the response the system is going to have to that force. But if you did not follow this specific part of the explanation, don't worry about that. This is going to be the general form of the particular solution. So we're going to do exactly what we did before. To find x, you have to plug in xp into the differential equation, right? The equation of motion that we got there, and you can find x from there. Once you got x, you can put all of them together and get the whole system response. So the whole system response, I'm just going to put these two together. A e to minus zeta omega nt sine omega dt plus phi plus x cosine omega t minus theta. This is a general form of the solution, including the homogeneous part and a particular part. Now, you can find x first by plugging in xp into the equation of motion. You can find x, very similar to the procedure we did for spring mass spring mass system. And once you find x, you can just put that uppercase S I'm talking about. Once you got this x, right, by doing that, you can put the whole equation or the suggested system. You can find the constants a and phi then. These are the only constants left after you find x by just applying initial conditions. Right? Given initial displacement x naught and initial velocity x dot naught, you can find a and phi. Now, I'm not going to go into details. I'll give you what these coefficients are if you follow this procedure. Right? Well, lengthy, and the procedure can be long. One of the main reasons I'm avoiding the process. But you will get these. You will get x as f naught over, if I'm not wrong, square root of omega n squared minus omega squared plus 2 zeta omega n omega squared. This would be x. Omega n being natural frequency, omega being the frequency of excitation, zeta being damping ratio. Theta would be, well, tan inverse 2 zeta omega n. Omega divided by square root of omega n squared minus omega squared. And let me write a bit of omega n. That would be theta. A and phi, well, phi would be tan inverse. Be ready, this is long. Omega d, I have to check that. X naught being initial displacement, minus x cosine theta, the whole thing divided by x naught dot plus x naught minus x cosine theta multiplied by zeta omega n minus omega x sine theta. And A, for that matter, would be, well, that is relatively simple. X naught minus x cosine theta divided by sine phi. So you need to find phi first to be able to find theta. So this is a pretty good length, I would say, set of equations. Keep in mind the system response is this. Right? With all these constants. As long as you know the frequency of excitation, natural frequency, which is pretty much, we can be fine knowing mass and stiffness. So let's rephrase it. As long as you know mass, stiffness, and damping constant, and you know the amplitude of the applied force, F naught, the uppercase F naught, and the frequency of excitation, you can actually calculate the system response and find how does the system respond to that given input force. Now, one important thing about this, we have two parts in this response, system response. Like one is coming from homogeneous part, one is coming from particular. Homogeneous solution, one is coming from particular solution. The part that is coming from homogeneous solution is called transient response. Transient response. And the part that is coming from particular solution is called steady state solution. Steady state response. Now, what do they mean by transient response and steady state response? I guess the name kind of gives it away a little bit. But what happens is that when you have a spring mass damper and you're applying a harmonic force, first few seconds, or depending on what system you're dealing with and what are the system's parameters, could be a fraction of a second. The very beginning of the motion, right? When you, let's say, you just start the system, or you just apply the force. First few seconds of the response, I would probably say not dominated, but includes transient response. So it has both a steady state response and transient response. After a few seconds, depending on how strong the damping is and what are the initial conditions, the transient response fades away, and the steady state response is the only response you have in your system. Again, after the first few seconds, let's say the system is working for hours, or after first fraction of a second, depending on, again, how does that system, what are the system parameters. So what I'm trying to say is that, let's put it this way, always graphs can be helpful. So if I say system response, let me write it this way. System response is equal to transient response plus steady state response. Right? That's what the equation was telling us. What does that mean? It means if I draw the transient response here, like some schematic way of looking at transient response. Remember, transient response is occurring or is happening because of initial conditions, right? That's the harmonic part of the solution. So you probably get something like this. This is an underdamped system. So you will probably get something along this line, not exactly this, right? It oscillates and it gets close to zero. So spring mass damper system, free vibration that we saw from before. Let me put it as x h t as time. Homogeneous part. The steady state part of the response is actually something that is constantly oscillating, and it's caused by the external force. So I'm separating these two parts of the response. The steady state response would be something like this. As the name says, it's a steady. It's, let's say, a cosine or sine. Well, probably it's more close to cosine, depending on what is the phase theta is. It can start from anywhere. But this would be xp. That's time. So the system response, the total response, is a combination of these two. Right? If you just add them together, probably I would say it's hard to, but then something like this happens. So after some few seconds, again, fraction of seconds or something, the transient response fades away, and what is left is the steady state response. If you look at that mathematical equation, right? This equation, system response. And the name says it is transient, so it's not going to last that long. So in so many cases, when we design structures to make sure that they can handle a specific type of vibration or study systems that are under vibrations, we can safely ignore the transient response. Because what if a system, when a system is working for hours, for days, for months, you turn on a pump and it's working for months or days, for weeks, the transient response becomes irrelevant. It happens at the beginning in first few seconds and then it's gone. It's not the case all the time. There are some situations that you have to take transient response into account, because sometimes transient response has a very huge amplitude and you have to make sure that your structure can handle that sudden huge amplitude of vibration at the beginning. So it's always good to take a look at it and see how big the response is. But in so many design cases, it's pretty established that you can just focus on a steady state response and see how does that affect your system.